So now it's my turn to summarize the next paper called Noise Tailoring for Scalable Quantum Computation by Randomized Compiling. I will stick more or less to the structure of the paper itself. First, introducing the different types of noises, errors and error rates. Then I will define what their method is, what the randomized compiling means. Then I will come to the advantages and probable usage. We're starting with a little motivation, why to change the type of error and how it's affecting the different error rates. The first way to quantify an error channel is the fidelity, also called infidelity or average error rate, and it measures the average deviation that an error channel induces on the system, and it could also be measured experimentally. On the other hand, the worst case error rate is defined as the diamond distance between the error channel and the identity. For error correcting codes in fault-tolerant quantum computation, it is important to have a low worst case error rate, because then you can make use of the threshold theorems. This means by reducing the worst case error rate, you can even reduce the error rate further. One can also estimate the worst case error rate depending on the average error rate. So you can experimentally measure the average error rate and you get upper and lower bounds for the worst case error rate. Depending on the dimension of your Hilbert space, the bound is more or less wide. Decoherence can be described by the so-called Pauli errors or Pauli noise. These channels are a stochastic mixture of the identity and the Pauli matrices. On the other hand, coherent errors or unitary errors are given by action of the unitary. It is beneficial to have Pauli noise compared to coherent errors because it has a lower worst case error, so it satisfies this lower bound on the estimation for the worst case error. One can also show that the thresholds are usually higher for Pauli noise. And another advantage is that the average error is scaling approximately linear in comparison to almost quadratically in the case of coherent errors. With the proposed method of randomized compiling, the coherent errors, or more or less arbitrary errors, can be turned into Pauli noise or stochastic errors. First, we divide a universal set of gates into easy and hard gates, where the easy gates are in this case the Pauli gates and the R gate. The hard gates contain the Hadamard gate, the control Z, square root of R, and pi eighth. We now divide our circuit into k rounds of easy gates following hard gates. In every cycle we have an easy set round of gates denoted by this vector, with each gate acting on one of the qubits, and the product of all the hard gates in this round denoted by gk. So it is important that we in the end have a stochastic channel. Therefore we take a twirling set T of the easy gates such that this averaged operation on the channel or on any channel will give a stochastic channel. Then the easy gates in every round are modified using a randomized or like a randomly chosen gate in the twirling set, such that in the end, what is applied is still the same gate in total. After all the gates applied, the resulting gate is the same, but the division is a different one. In the end, we are randomly sampling over multiple runs where we choose those twirling gates in every round independently. This is why it's called randomized compiling, because the gates that are implemented are chosen randomly. One can now really prove that the resulting channel is a stochastic one. So assuming that the noise is gate independent on the easy gates, but still can depend on the hard gates, we can show that the error channel in every step, if we randomly sample, is a stochastic channel. Of course, in these equations we use that the easy gates are twirled in the way that we defined before. For the last steps and also for measurement, we insert a Pauli gate, and according to which Pauli gate was chosen, we can change the measurement outcome so that it fits in the end. If the errors also depend on the easy gates, then we can estimate the distance to the gate independent circuit by the distance of the averaged error channel to the individual error channel. In more specific cases, one can even estimate this further. The method is tested with unitary errors starting in the computational basis state. They averaged the different error rates for a variety of instances. They found that the worst case error was reduced by a factor of 2. They also measured the variational distance, so they took the difference of the projection into every state. They found that because of the approximately linear scaling with the circuit depth, it's more important to reduce the local errors at every location. This is achieved by this randomized compiling technique, turning all the errors at every error location into stochastic noise. Now we want to do a bit of a discussion of the proposed method. Previously there has been a proposal to use randomized Clifford gates, so in some sense this new method can be seen as an extension of this proposal. Another method used to deal with the coherent errors is the Pauli random error correction, but this seems to have problems with multi-qubit gates. And so far we also only considered noise that can be described by a channel, and they also raised the question if this may be robust also to non-Markovian noise. But more importantly, I think, is the use in fault-tolerant circuits, where we can reduce the worst case error rate to get a better threshold and also a better scaling of the error rate. So in the end we see that this method is applicable in various situations. It seems also beneficial to use them together with fault-tolerant circuits. So thank you for listening, and I would be happy trying to answer all of your questions.